Yeah, welcome you all for this section of this course. This is week 2, lecture 1. Topic: analysis of continuous beam without sinking of supports. Analysis of continuous beam without sinking of supports. We'll see. So these are the lecture outcomes. So after completion of this lecture, student will be able to calculate the fixed end moments for the different types of loadings, and student will be able to analyze the continuous beam by slope deflection method of analysis. Now we'll see one problem related to this analysis of continuous beam with one overhang. In the previous class, we discussed about the analysis of continuous beam with the two extreme ends are fixed. So this problem we are discussed in the previous CDT, that is CDT3. Now in this problem, in this session, in this lecture, we'll try to discuss about one overhanging problem. So if overhang is there, overhang is subjected to 40 kN load. So how to analyze by using the slope deflection method of analysis? We'll see here. Okay, right. So now we'll see the figure. This is a continuous beam. We have three spans. We have span AB, span BC, as well as span CD. Span AB subjected to uniform distributed load, of 20 kN per meter, and its moment of inertia for the AB span is 2I. For the BC span is subjected to 80 kN load. This is a concentrated load. Symmetrical point load is acting. There is 80 kN is acting at a distance of 2 meters from the support C. So moment of inertia BC member is high, and for CD member, moment of inertia is high, and it's subjected to the point load of 40 kN is acting. Now, so is asked to analyze by using slope deflection method of analysis. By using slope deflection method, we need to analyze. So slope deflection method, which method? This is a displacement method. So in this displacement methods, unknowns are the displacement, that is slope and deflection. Slope and deflection. Theta and delta. Theta and delta are the unknowns. So if you observe, the theta at A is 0 because the fixed support. Theta B is the unknown, and theta C is also unknown. So those are the unknowns. And the delta for all the supports A, B, C, D all are 0. Delta at A and delta at B and delta C is 0. So for the analysis, first step for the analysis of continuous beam by using slope deflection method of analysis, the first thing what we need to do is we need to calculate the fixed end moments. We need to calculate the fixed end moments for the given load. For the given loading, we have to calculate the fixed end moments. Okay. So if you observe, the first span is subjected to uniform distributed load throughout its span. So entire span is subjected to uniform distributed load. The intensity of uniform distributed load is 20 kN. Okay. So now how to calculate fixed end moment? Beam is subjected to uniform distributed load. Then how to calculate fixed end moments? So fixed end moments can be calculated. So this is minus WL square by 12. Let us say this is A and it is B. MFAB is fixed end moment at AB will be equal to minus WL square by 12. MFBA will be equal to plus WL square by 12. Yeah, right. Here for the AB span, W is equal to 20, L is equal to 6 meters. Okay, if you substitute it, you're going to MFAB will value minus 60 kN. MFBA is equal to plus 60 kN. Now consider BC span. If you take BC span is subjected to a concentrated load of 80 kN is acting. Okay, the symmetrical point load. For the symmetric point load, We can calculate fixed moments. MFBC will be equal to formula is WL by 8 minus WL by 8. This is plus WL by 8. MFCB is equal to plus WL by 8. MFCB is equal to plus WL by 8. Substitute W is equal to 80 and L is equal to 6. L is equal to 4 actually. So L is equal to 4. W is equal to, okay, minus WL by 8 and plus WL by 8. So you're going to get, substitute the W value and L value. You're going to get BC is equal to minus 40 and MFCB is equal to plus 40 kilonewton meter. Now consider for the CD member. For the CD member is subjected to 40 kilonewton load. Okay. So now calculate the end moment. So end moment is not there. End moment directly we can write the moment here. That is 40 kilonewton meter. So for this, any fixation will not be there because at C is a roller support. It will not take any moment. It will not take any moment. So that's why at C moment summation of moment at C will be 0. But applied moment is there. Resisting moment is 0, but applied moment is there. So applied moment will be 40 into 2, that is 80 kilonewton meter, which is acting in the anti-clockwise direction. Which is acting in the anti-clockwise direction. Okay. So after calculation of this fixed moments, the second step we need to develop slope deflection equation. We need to develop the slope deflection equations. So we need to develop slope deflection equations. Okay. We have tried the slope deflection equation. MAB will be equal to, the formula is MFAB plus 2EI by L into 2 theta A plus theta B minus 3 delta by L. So this is the equation of slope deflection equation for the AB span. If you see the span, just now we discussed theta A 0, theta B and theta C are the unknowns. So remaining all zeros. Substitute theta A is equal to 0, theta A is equal to 0, and delta is equal to 0. Then theta is equal to 0 and MFAB substitute minus 60. In place of I, you substitute 2I. Why? Because first span is first span moment of inertia is 2I. First span moment of inertia is 2I. Substitute it. And theta A is also 0. Theta B is there. So delta is 0. So you will going to develop MAB will be equal to, final moment MAB will be equal to minus 60 plus 2 by 3 EI theta B. You consider equation number 1. Now similarly you apply for MBA. MBA is equal to, the equation of slope deflection equation MBA will be equal to MFBA, fixed moment due to loading, plus 2 EI by L into theta B, 2 theta B plus theta A minus 3 delta by L. So this is the formula. But theta A is equal to 0 and delta is also 0. Substitute theta A is equal to 0, 0. I is equal to 2I. Substitute I is equal to 2I. MFBA will be plus 60. Plus 60. So calculate. So you're going to develop MFBA is equal to this concept. MBA will be equal to plus 60, 4 by 3. Yeah. So you consider equation number 2. So similarly, you write for span 2, that is MBC. Second span 80 kilonewton is active. For second span 80 kilonewton is active. The distance is 2 meters. So for this, theta B is unknown and theta C is also unknown. This is roller and that is also roller. Okay, this is roller one. In given figure, given problem, this is roller and this is also roller. So this is theta C is unknown, theta B is also unknown. So MBC is equal to MFBC 2A by L 2 theta B plus theta C minus 3 delta by L, delta value 0. Okay. Substitute it, you are going to get, this is equation number 3, MBC. Similarly for MCB also, MCB. So C will going to get factor 2 and B will go to factor 1. So substitute delta is equal to 0, you are going to get the MCB value. MFCB and MFCB value substitute and delta value substitute. Theta B is unknown, theta C also unknown. You are going to develop another equation. This is equation number 4. So we have developed 4 equations. So this is the step 2. Coming to step 3. Coming to step 3, we need to form the joint equilibrium equations. We need to form the joint equilibrium equation, that is summation of moment at joint B equal to 0. This is one of the joint equilibrium equation. So our given figure, this is our given figure. It will be summation of moments at B will be equal to 0. That means MBA plus MBC will be equal to 0. MBA plus MBC equal to 0. You use this condition for solving theta B value. MBA plus MBC equal to 0, you're going to get you're going to develop an equation in terms of theta B and theta C. This is, you consider equation number 5. And if you see at C, again we need to develop one joint equilibrium equation, that is summation of moments at C will be equal to 0. Summation of moments at C equal to 0. That means MCB plus MCD will be equal to 0. MCB plus MCD will be equal to 0. What is MCD? MCD, applied moment is there. So this is 2 meters, 40 kilonewton. MCD is producing 80 kilonewton, that is which is producing sorry, 1 second, I'll see. Yeah, right. So 40 kilonewton is producing, that is clockwise movement, but resisting movement will be anti-clockwise. So resisting movement will be anti-clockwise. So we need to consider that as negative. We need to consider that as negative. Okay, MCB, MCD, this is a resisting movement, that is MCD due to resisting movement. For balancing this applied moment, so we one moment will going to develop, that is MCD is minus 40 into 20, that is minus 80 kilonewton. MCB is equal to 80 kilonewton. MCB is equal to 80 kilonewton. Okay, MCB will be equal to 80 kilonewton. So balancing that, okay, we substitute from equation number 6 and 5, we will going to get EI theta B is equal to 19.2. Substitute EI theta B value in equation number 1, 2, 3, 4. Substitute equation number 1, 2, 3, 4. So substitute it. You will going to form the final end movements. You will going to get the final movement. So MAB is equal to this value, MBA is equal to this one, MBC is equal to this one, and MCB is equal to this value. So all values, final movements values, you are going to get. Okay. So this is the calculation. So thank you one and all.